might be a good time to restart. I guess next up is Nastaran. Nastaran, are you there?
Hi, yes, I am. Just a second, I think the
Okay, great.
camera is not. Just a second.
I guess while Nastaran is getting prepared, as Hao Song said, the previous paper was published in ISCA this year, so you're really seeing some cutting-edge research published at top conferences, which is part of the role of this course. And Nastaran is going to talk about her work that was also published in ISCA in June in 2020. So it's also cutting edge. And she's a PhD student working with me, although she's in a very different time zone right now. So hopefully she will not fall asleep while delivering this lecture. I guess you're 10 hours or 9 hours behind.
It's 6:44 a.m. precisely here.
Okay, it's not that terrible.
You will
then.
see the sunrise in the window here, hopefully
Okay.
during the lecture.
I guess that's not that bad. Could have been 3:44.
Yes, true.
Okay, so Nastaran is going to talk about the virtual block interface, which is a very innovative way of thinking about or rethinking virtual memory. And I think this sort of research is very much needed going into the future. It can enable many interesting things as opposed to sticking to the business as usual with virtual memory that has been around for more than 50 years, as you know. And hopefully Nastaran will give you why it could be very exciting. Go ahead, Nastaran.
Thanks for the introduction. Yeah, just a quick background, a little bit more information about why it is an exciting direction to look into. So as you know, modern compute, before I start my presentation, I like to motivate generally this direction. So as you know, modern computing systems in all varieties of use cases heavily depend on the virtual memory to provide many features, of which all of them are integral to the overall performance and functionality of the system. But the problem is that virtual memory is facing important challenges today that puts efficiently maintaining this critical component as it is at a serious risk. And that is mainly due to the fact that the virtual memory was originally designed around 60 years ago, not having the diversity and the complexity of today's computing systems in mind. So as a result, while the core concepts of virtual memory that were developed decades ago have remained mainly unchanged, the nature of the other components of the system, for example, the workloads, as well as the hardware architecture in today's systems have changed significantly over the years. This mismatch between the existing virtual memory design and the other contiguously evolving and diversifying components of the system has led to the virtual memory officially becoming a performance bottleneck in modern computing systems. So efficiently addressing this problem will become even increasingly more necessary as the complexity and also diversity in computing systems is increasing every day. We are not the only one noticing that. The importance of this problem is evidently acknowledged by both the research community in academia and industry, considering the wide body of research and innovation that aims at alleviating all the overheads of the conventional virtual memory design when adopting the diversity in modern computing systems. But the problem is that while these prior works built extensive optimizations and adjustments to the conventional virtual memory framework, no prior work actually looks into fundamentally rethinking the virtual memory design in order to make it more suitable for today's systems and future workloads and architectures. So this work that I'm going to present today is our first step towards this direction, and I'm excited to present it to you guys. Let me share my screen. Okay. I think that's... So do you guys see the slides now?
Yes, it looks good.
And hopefully the slides, not the presenter view, the messy presenter view.
That's good.
Okay, good. So yeah, the work that I'm going to present is the virtual block interface, a flexible alternative to the conventional virtual memory framework. So to begin, I will give a high-level summary of the talk. The motivation of this work is that modern computing systems continue to diversify with respect to system architectures, emerging memory technologies, and applications memory needs. Unfortunately, continually adapting the conventional virtual memory framework to each possible system configuration is challenging, as I just described, and often results in performance loss or requires non-trivial workarounds. So our goal is to design an alternative virtual memory framework that efficiently supports a wide variety of new system configurations and provides the key features of the conventional virtual memory framework while eliminating its key inefficiencies. To this end, we propose Virtual Block Interface, a novel alternative virtual memory framework that delegates the physical memory management to a dedicated hardware in the memory controller. VBI efficiently adapts to different and increasingly diverse system configurations, and it also reduces the overheads and complexities related to the conventional virtual memory framework. The memory controller-based memory management in VBI leads to many benefits, some of them not easily attainable in existing virtual memory framework, such as low overhead page walks in virtual machines and inherently virtual caches. We demonstrate the benefits of VBI with two concrete use cases. First, we experimentally show that VBI significantly improves performance for both native execution and virtual machine environments by 2.4 times and 4.3 times respectively. Second, we show that VBI significantly improves the effectiveness of heterogeneous main memory architectures. Here is the outline for my talk today, and I will start with explaining our motivation for this work. Virtual memory is a core component of the modern computing systems, and it was originally designed, and it has remained mainly the same since its inception, and was originally designed for systems whose memory hierarchy fits a simple two-level model of a small but fast main memory and a large but slow external storage. In such a configuration, the OS can easily abstract away the underlying memory architecture details and present the applications with a unified view of the memory. However, the modern computing systems no longer follow this model and continue to diversify significantly. For example, with respect to emerging memory technologies and architectures, new system architectures, and diverse memory requirements of modern applications. Therefore, the OS must now efficiently adapt to the wide range of application memory requirements that leverage the advantages offered by emerging memory architectures and new system designs while simultaneously hiding the complexity of the underlying memory and system architecture from the application. Unfortunately, this is a difficult problem to tackle in a generalized manner and often results in performance loss or requires non-trivial workarounds. As a result, continuing to adapt a conventional virtual memory framework to today's diverse system configurations is challenging. Before diving into these challenges, let's take a look at the conventional virtual memory design. So this picture here shows the virtual memory management in Intel x86 as an example of a conventional virtual memory framework. In such a framework, each process is mapped to a single private virtual address space of fixed size, for example, 256 terabytes in Intel x86. The operating system in conventional virtual memory framework controls the access permissions by managing the one-to-one mapping of processes to their specific virtual address space. The OS defines the mapping from each process's virtual address space to the physical memory and stores both the mapping information as well as permission information in a set of per-process page table. The page tables are managed by the operating system and read by the memory management unit in the processor to perform the address translation. This design suffers from many fundamental challenges when adapting to modern and diverse system configurations. Here I describe three examples of such challenges. The first example is related to the inflexibility of the conventional virtual memory framework in adapting to the modern application's memory requirements. So prior works show that many applications can reduce the address translation overhead using flexible page tables that are customized to the application's actual memory footprint and access patterns. However, in conventional virtual memory frameworks, while the OS defines the virtual to physical address mapping in the page tables, the hardware must be able to read these tables to perform the address translation. This arrangement requires using rigid address translation structures that are shared between and also understood by both the hardware and the OS. For example, the 4-level page tables of fixed granularity in Intel x86 are good examples of such rigidity. As a result, implementing the page table flexibility that applications can benefit from is challenging due to the rigidity of the conventional virtual memory design. Another challenge exists when adapting the conventional virtual memory framework to virtualized environments. In a virtualized environment, the guest OS is running on top of the host OS in a virtual machine. In such a setting, the guest OS is unaware that it is running in a virtual machine and performs memory management on the emulated physical memory and translate the guest virtual address to the guest physical address, which is in fact the host virtual address. The host OS then performs a second round of memory management by mapping the host virtual address to the host physical address. This extra level of indirection results in many important issues, including the two-dimensional page walks, where the number of memory accesses required to perform address translation increases dramatically. This issue makes it challenging to perform computation in virtualized environments efficiently. The third challenge that we discuss here arises when managing heterogeneous memory architectures. Enhancing performance with heterogeneous memories requires first dynamically mapping data to different physical memory regions according to application requirements. For example, mapping frequently accessed data to the fast memory, and second, by migrating data when those requirements change. Since in conventional virtual memory framework, the OS defines and manages address mapping, efficiently implementing such functionality faces fundamental issues that the OS has low visibility into fine-grained runtime memory behavior information. Therefore, it becomes challenging to make timely decisions based on quickly changing memory access patterns or other dynamic behavior. Considering the key role that virtual memory has in the overall performance of the modern computing systems, a wide body of research proposed mechanisms to alleviate the overheads associated with the conventional virtual memory design. However, despite notable improvements, these solutions suffer from two major shortcomings. First, they are mainly designed based on specific system or workload characteristics, and as a result are applicable to only a limited set of problems or applications. And second, each solution requires a specialized and not necessarily compatible changes to both the operating system and the hardware. And as a result, implementing these proposals at the same time in one system is a daunting prospect. This highlights the need for a holistic solution to efficiently support today's diverse system configurations. In response to the need for a holistic solution, our goal is to design an alternative virtual memory framework that has two properties. First, to efficiently and flexibly support increasingly diverse system configurations, and second, to provide the key features of the conventional virtual memory frameworks while eliminating its key inefficiencies. I will now describe the key idea and the guiding principles of the VBI framework. Considering the challenges that the conventional operating system managed virtual memory framework faces, the key idea in VBI is to delegate the physical memory allocation and address translation to a dedicated hardware in the memory controller. To this end, the VBI design is driven by three key guiding principles. First, programs should be allowed to choose the size of their virtual address space. This mitigates the address translation overhead associated with unnecessarily large and fixed-size virtual address space in current systems. Second, address translation should be decoupled from memory protection, as they are logically separate, and this enables opportunities to remove address translation from the critical path of an access protection check and deferring the address translation until physical memory must be accessed, thereby lowering the performance overhead of the virtual memory. It also enables the flexibility of managing address translation and access protection using separate structures customized to the requirements and characteristics of the process. Third, software should be allowed to communicate semantic information about application data to the hardware. As shown by prior work, conveying data semantic to the hardware helps hardware to manage the underlying resources more intelligently. I will now describe an overview of VBI and how these principles are implemented. This figure shows an overview of the VBI design compared to the conventional virtual memory framework. Now I will describe how VBI enables its key idea, which is delegating the address translation and memory allocation duties to a dedicated hardware in the memory controller. VBI introduces a globally visible address space called a VBI address space, which consists of a large set of virtual blocks of different sizes from a set of predefined size classes, which you see an example of it here. All the virtual blocks are visible to all processes running on the system, and processes map each semantically meaningful unit of information, such as a data structure or a shared library code, to a separate virtual block of appropriate size. The key idea of the VBI design is enabled by the fact that the globally visible VBI address space provides VBI with system-wide unique VBI addresses, which can be directly used to access unchipped caches without requiring address translation. As a result, according to the key idea, the address translation and memory allocation can be deferred until necessary to access the physical memory. To this end, the address translation and physical memory allocation are delegated to a hardware-based memory translation layer in the memory controller. In VBI, the OS no longer needs to manage the address translation and memory allocation for the physical memory devices. Instead, it retains full control over access protection by controlling which program have access to which virtual block. In order to access a virtual block, a process needs to be attached to that virtual block with the right permissions. To this end, the OS attaches the processes to the requested virtual blocks and stores the list of virtual blocks attached to each process and their associated permissions in a per process table. OS performs access protection using this table to ensure that the process has enough permissions to access the requested virtual block. In contrast to the conventional framework, where each process is mapped to a single fixed-size virtual address space, irrespective of the actual memory requirements of the process, in VBI, any process can attach to any virtual block. Accordingly, the process's total virtual address space is defined by the set of virtual blocks that are attached to the process. In other words, by the process's actual memory needs. This satisfies our first guiding principle. Additionally, in contrast to the conventional design where the OS manages both access protection and address mapping, VBI decouples the two by delegating the address mapping and address translation to the memory translation layer, while allowing the OS to retain full control over access protection by controlling the mapping between the processes and the virtual blocks. This addresses our second guiding principle. Decoupling address translation and access protection allows VBI to maintain address translation information in a separate structure than access protection information. This relaxes the constraint of sharing address translation structures with the OS, which exists in the conventional framework. Therefore, in contrast to the conventional framework, VBI enables the flexibility to employ different types of translation structures customized to the application's needs. Accordingly, VBI maintains a separate translation structure for each virtual block and can tune it to suit the properties of the virtual block. For example, single-level tables for small virtual blocks or those with many large contiguously allocated regions. Each virtual block in VBI is also associated with a set of information, including a bit vector that indicates the semantic and access properties of the virtual block's content, such as access pattern, latency, or bandwidth sensitivity. The properties bit vector associated with each virtual block enables VBI to implement the third guiding principle by communicating the memory requirements and semantics of the data that the virtual block contains to the hardware. I will ask you guys to refer to our paper for more information, including a detailed reference implementation and microarchitecture of VBI. I will now describe the optimizations that VBI enables. So VBI naturally enables a variety of important optimizations which are not easily attainable in the conventional virtual memory framework. We discussed 7 examples of such optimizations in our paper, 3 of which are already achieved through our guiding principles. I will explain 3 other examples of these optimizations now, and please refer to our paper to read about another example of such optimizations. Just a second, sorry, I don't know why the slides are, okay. Now I will have a look at, let's take a look at the first example optimization. A common approach to address on-chip caches in the conventional framework is virtually indexed, physically tagged. In this approach, the core issues virtual addresses to the cache while the physical address is retrieved by accessing the TLB in parallel to the cache index probe. In case of a TLB hit, the physical address is used to perform the tag lookup, and in case of a TLB miss, a page walk is required to retrieve the physical address required to access the cache. In order to remove the overhead of address translation for cache accesses, virtually indexed, virtually tagged caches access the cache using virtual addresses only, without requiring the address translation. And address translation is performed prior to accessing the physical memory. Therefore, VIVT caches reduce the address translation overhead by reducing the number of address translation requests. However, most modern architectures do not support virtually indexed, virtually tagged caches due to 2 main reasons. First, since virtual addresses are not globally unique in conventional systems, VIVT caches suffer from synonyms and homonyms. And second, although address translation is not required to access VIVT caches, the access permission check required prior to cache accesses still necessitates accessing the TLB and can induce a page table walk on a TLB miss. This is due to the fact that the protection bits are stored as part of the page table entries for each page in the current system design. VBI addresses both these issues together. So first, VBI accesses all on-chip caches using VBI addresses. Since VBI addresses are unique system-wide, they eliminate the possibility of synonyms and homonyms. And also second, VBI decouples the protection checks from address translation by storing protection permissions in a different structure. And in a separate set of tables, which delegates the access permission management to the OS and avoids the need to access transition structures for protection purposes. As a result, VBI reduces the address translation overhead by naturally enabling virtual caches without their known complexities in current systems. I will now describe the second optimization example. As I mentioned earlier, in virtually tagged physically indexed caches, the physical address is required to access the cache, which needs the data to be already mapped and allocated in the physical memory. On a cache miss, then the actual cache line is looked up and returned to the cache. In VBI, in contrast, all on-chip caches are inherently virtual and are directly accessed using the system-wide unique VBI addresses without requiring address translation. As a result, the physical address is not needed to access the cache, and therefore the cache line does not need to be mapped and allocated in the physical memory prior to being accessed in the cache. VBI exploits this opportunity and delays the allocation of physical memory for virtual blocks until it is necessary. Accordingly, on a cache miss, if the MTL realizes that there is no memory allocated for the requested cache line, it simply returns a 0 cache line for that virtual block. And on the right back, the MTL defines the VBI address to physical address mapping for the virtual block and allocates the VB in the physical memory. The delayed physical memory allocation provides VBI with many benefits that are not easily possible in the conventional virtual memory framework. For example, first, it eliminates the address translation for accesses to the regions that are not yet allocated, which reduces the address translation overhead of the system. Second, it eliminates the original memory, It eliminates the original memory request from accessing the memory as well by returning a zero cache line for accesses to the regions with no memory allocation, which results in improving the overall system performance. And finally, it avoids allocating memory for smaller VBs that may never leave the cache during their lifetime, which reduces the memory footprint of the process. As a result, by enabling delayed physical memory allocation, VBI reduces the address translation overhead, improves the overall system performance, and reduces the total memory consumption of the process. I will now describe the third optimization example. As I mentioned earlier, the conventional virtual memory framework suffers from two-dimensional page walks where both guest and host OS perform address mapping. VBI, however, resolves this issue. In VBI, the guest and the host OS interact once to attach the process running on the virtual memory to its virtual block. Once attached, any memory access from the virtual machine directly uses a VBI address to access the caches, and the address translation is performed only at the memory translation layer in the memory controller. As a result, unlike existing systems, address translation for a virtual machine under VBI is no different from that for a host. Therefore, by eliminating 2D page walks, VBI reduces address translation overhead in virtualized environments. I will next discuss the methodology for testing VBI and evaluating our mechanism. For our evaluations, we use a heavily customized version of Ramulator to faithfully model all components of the memory subsystem, including TLBs and page tables. We have released this modified version of Ramulator as well. Our workloads consist of benchmarks from Spec 2006, Spec 2017, Tailbench, and Graph 500, and here is a summary of the main parameters for our simulations. I will now present the results, which includes two use cases. We evaluate VBI for two emerging and important use cases. In the first use case, we evaluate how VBI reduces address translation overhead in native and virtualized environments. We evaluate the performance of 7 baseline systems and 3 different VBI configurations. Here we present results for 3 baselines and 1 VBI configuration, and for the rest of the results, you can refer to the paper. The baselines that we present here are native, where applications run natively on an x86 system, virtual, where applications run inside a virtual machine, and perfect TLB, which is an unrealistic version of native with no address translation overhead. We also show results for VBI full, which is VBI with all 7 optimizations that I mentioned earlier. This figure compares the performance of virtual VBI full perfect TLB systems normalized to the native configuration. We make 6 observations. First, virtual reduces performance for 44% on average compared to native due to the two-dimensional page table walk issue in the conventional framework. Second, perfect TLB improves the performance compared to native by 1.9 times on average by removing the address translation overhead completely. Third, VBI full improves the performance by 2.4 times on average compared to native by enabling all 7 optimizations that we explained earlier. And fourth, VBI full improves the performance by 4.3 times on average compared to virtual. This is due to the fact that in contrast to the conventional framework, in VBI, the address translation overhead for the processes running inside the virtual machine is no different than the processes running natively on the host. And as a result, VBI enables significant performance improvements in virtualized environments, which is not attainable with the conventional virtual memory framework. The fifth observation is that VBI outperforms the perfect TLB system by 49% on average. This is because the benefits of VBI and the optimizations that it enables is not limited to only reducing the address translation overhead. The delayed physical memory allocation mechanism, for example, reduces the overall system performance by reducing the traffic to the main memory. You can refer to the paper for more details about how VBI can outperform the perfect TLB configuration. We make the conclusion that VBI can significantly improve performance in both native execution and virtual machines. For the second use case, we evaluate the benefits that VBI offers in harnessing the full potential of heterogeneous memory architectures, which are tightly dependent on data mapping and migration. To this end, we evaluate a hybrid PCM DRAM memory architecture for which we examine 3 different systems. The first one is hotness unaware PCM DRAM, where the mapping mechanism that is unaware of the data hotness or the frequency of accesses to different regions of the memory. VBI PCM DRAM is the configuration where VBI maps and migrates frequently accessed virtual blocks to DRAM as the fast memory in the heterogeneous memory architecture. And the third system is ideal, that is an unrealistic mapping mechanism which uses Oracle knowledge to always map frequently accessed data to the DRAM. This figure compares the performance of VBI PCM DRAM and ideal normalized to hotness unaware PCM DRAM. As we can see, VBI PCM DRAM improves performance by 33% on average compared to the hotness unaware PCM DRAM by accurately mapping the frequently accessed data structures to low latency DRAM. We observe similar benefit when using VBI in systems such as tiered latency DRAM, which is another heterogeneous memory architecture. You can refer to the paper for some information regarding that evaluation. We conclude that VBI is effective for enabling efficient data mapping and migration in heterogeneous memory systems by conveying the data semantics to the hardware and enabling more intelligent management of memory resources, something that is not possible in the conventional virtual memory framework. Now let me conclude by giving the summary. We introduced the virtual block interface, a new virtual memory framework to address the challenges in adapting conventional virtual memory to increasingly diverse system configurations and workloads. The key idea of VBI is to delegate memory management to hardware in the memory controller. The memory controller-based memory management in VBI leads to many benefits not easily attainable in existing virtual memory, such as inherently virtual caches and avoiding two-dimensional page walks in virtual machines. We experimentally show that first, VBI significantly reduces overhead of address translation by reducing the number of translation requests and associated memory accesses. And second, increases the effectiveness of managing heterogeneous main memory architectures. We conclude that VBI is a promising new virtual memory framework that can enable several important optimizations and increase the design flexibility for virtual memory. We believe and hope that VBI will open up a new direction and many opportunities for future work in novel virtual memory frameworks. Thanks for listening to the talk, and I look forward to your questions.
It looks like there's a question in the chat, Nastaran.
Yeah, if I just a sec. How can the OS map a peripheral into the virtual addresses space memory mapped IO using VBI? That's an excellent question. So the way that VBI basically takes care of that is easily by mapping the region of the memory that is considered memory mapped IO to one single virtual block. And every time that there's an access to that region of the memory, OS will directly access the physical memory because that virtual block is marked as a memory mapped virtual block. So that's how we take care of that. And there's also more information about that in the paper. Is it correct that VBI is incompatible with ASLR because all processes use the same VBI addresses? I don't see where the incompatibility can come from, but all processes use the same VBI addresses. So it's an interesting question because there's something in VBI design that was not directly covered in this presentation. So because we were aware of the challenges that arise when you expose a globally unique virtual address space to processes similar to, for example, single address space OSs, we actually introduced a level of indirection between the unique VBI addresses, which is globally visible to the hardware and, for example, on-chip caches, and the operating system, between that and the address space that processes see. So in VBI design, instead of exposing that VBI address space to the processes, we actually, when a virtual block is attached to a process, it is contained, this information is contained in a set of tables, per process table, as I mentioned. And instead of giving that process the VBI address or the ID of that virtual block, we actually give the process the entry, the index to the entry of that virtual block in that table. So every time that process needs to access a virtual block, instead of specifying the virtual block VBI address, what they do is that they ask to access that entry of their table, which called CVT, that contains all the virtual blocks that are attached to that process. It basically points to the entry, because the only thing that process has is the index to that table, and says that I want to access this virtual block, and this is the offset in that virtual block. So basically, VBI addresses are not exposed to the processes, and that's why they do not see a unified addresses space that all of them have access to it. I hope that answers your question. In the meantime, if we have a couple of minutes, and while I'm waiting to see your questions, I'd like to mention a couple of directions that we are considering, and also the importance of research in this direction. So this paper proposes a solution for a significantly important and difficult and also famous problem, which is preserving the virtual memory abstraction when adopting the diversity in modern computing systems. And by targeting such a critical issue, we hope that our paper triggers research around an important topic that results in impactful outcome. And in the long term, the problem, as I said, the problem of efficiently preserving the virtual memory abstraction becomes even more significant because of the ever-increasing diversity and complexity in modern computing systems. So we hope that this research will stimulate more important research in this direction. And also, considering the fact, the other important aspect of this research is the fact that conventional virtual memory frameworks are traditionally managed by the operating system, which requires a cooperation of operating system and the hardware in a rigid way. And our paper makes a case for a better partitioning of duties between the hardware and the operating system for the virtual memory design. And the hope and goal is to achieve a more efficient and flexible virtual memory framework and memory management. And in the long term, we believe that this paper can inspire more intelligent and more important research in better partitioning of duties between hardware and software, and also more importantly, looking into the optimizations that such a optimized partitioning of duties can enable. And also we hope that as the first paper that introduces a hardware-based virtual memory framework, we will also inspire and all the optimizations and benefits that it enables, which some examples of it are mentioned in the paper. We hope that we also inspire research in that direction, which we believe there are a lot of opportunities there. I don't see any more questions, but I invite you to send me an email if there's anything that you guys need to discuss, or if you're interested for more discussion on this topic. I'll be happy to have that. Yep.
I have one more question. I didn't quite understand how the process isolation works, because I mean, now you have this many-to-many mapping, and this is,
Yes.
How do you make sure that one process cannot access data from the other process?
Yeah, excellent question. So the way that it works is that we basically, as I mentioned, OS manages a per process table that identifies the virtual blocks that are attached to that process. Basically, a process is not allowed to access any virtual block unless it is first attached to that process. The virtual block is attached to that specific process. And second, it has enough permissions to access that virtual block. So what happens is that when there's a memory access to a virtual block from a process, the first thing that happens is that we first check that if that OS checks if that process actually have that virtual block in its table, which means that it is attached to that process. If that is the case, we check if the offset of the memory access is actually within the size of the virtual block, so that we make sure that it is not accessing somewhere else in the memory, which the process is not supposed to. And the next thing that happens is to check the permissions for that memory access to make sure that, for example, if it's a write request, that process has actually enough permissions to that virtual block to make write memory access to that region. Does that answer your question?
Yes,
So
I guess it sounds like there's quite some overhead, but I might be a bit suspicious, but it's an early approach, so I won't be too critical.
So actually, that's a very good point, because it actually highlights one of the benefits of decoupling address translation from memory protection. So if you think in the conventional way that access protection information were stored in the page tables at 4K byte granularity or 2 megabyte granularity, for the data structure that is maintaining the access protection information is the same as address translation, right? So it has to be at a fine granularity, which is not really necessary. So what VBI does is that we observe that naturally access protection should be unified across one single memory object for each process, right? So in VBI, what we do is that we store access protection information in that table that I mentioned at the granularity of virtual block. So what that means is that instead of having that table at a granularity of 4 kilobytes, we now have it at a much larger granularity, which reduces the number of entries, which as a result simplifies the structure that access protection information is maintained using, right? So what we observed is that on average, most of our workloads that we evaluated in this paper needed something, if I'm not mistaken, around 40 entries on average to maintain the virtual blocks that they are attached to, which looking up a table of 40 entries only is much more efficient than looking up page tables to access protection check in conventional virtual memory framework. So that is one way of making sure that the overhead of access protection is not significant in VBI.
Okay. Yeah, these are quite interesting results. Thank you.
Thank you.
Okay, I think we can discuss more, but this is probably a good time to finish up. Thanks, Nastaran. And I think there's a lot, this definitely opens up a lot of research, and there are many questions that may come to your mind. I would suggest reading the paper, because the paper actually contains answers to many of those questions. And if you find something that it doesn't contain answers to, then you can talk with Nastaran also. That could be a good research topic potentially.